So we're going through the answers to the extra questions on equilibrium, where you're trying to calculate Kc values from equilibrium concentrations. So in the first side, we got 5 questions, all pretty similar, calculating Kc. So the first one is an equilibrium between N2O4 and NO2. So what I might do is just go ahead and just make a Kc expression, just because I know I'll need it later on. So on top, we're going to have NO2 concentration squared over the concentration of N2O4. Units, it's going to be moles per decimeter cubed squared over moles per decimeter cubed, which is just the same thing as moles per decimeter cubed. So if I look at what information I've got, so if I do my wee table, so I need my initial moles, reacting moles, equilibrium moles, and in this case, I do have units for Kc, so I'm going to need to use concentrations. So I'm going to calculate my equilibrium concentrations. And that's for N2O4 in equilibrium with NO2. So in terms of what I've got in the question, I'm told that at the start I've got 0.4 moles of N2O4. Plonk that in there. Doesn't seem to be anything about starting with some of the product, so I'm assuming there's nothing there. And at equilibrium, there's found to be 0.1 moles of N2O4 in the gaseous mixture. So I've ended up with 0.1 moles at equilibrium. If I start with 0.4 and then ended up with 0.1, I must have reacted 0.3 moles of it. So I've used up 0.3. Therefore, I need to work out how much NO2 I made from that. It's a 1 to 2 ratio. Therefore, if I used up 0.3 moles of the reactant, I probably made 0.6 moles of the product. So if I started with none of it, and then I made 0.6 moles of it, I've ended up with 0.6 moles of the product. For it into a concentration, I need to do a wee division. I need to use concentration as number of moles over volume. So that can be dividing by 0.5, because that's the volume given in the question. 0.1 divided by 0.5 is just 0.2 moles per decimeter cubed. And then for NO2, 0.6 divided by 0.5 is just 1.2 moles per decimeter cubed. So bringing this to my expression, Kc equals NO2 squared, which is 1.2 squared, over N2O4, which is 0.2 squared, which equals 36 moles per decimeter cubed. Moving on to the second question, it looks very similar. In the reaction, SO2 plus O2 going to SO3 and gives you some equilibrium concentrations and a volume. So equilibrium is this. I'm going to make my Kc expression just at the start. So Kc equals SO3 squared over SO2 squared times O2. Units is going to be moles per decimeter cubed squared over moles per decimeter cubed, which is moles per decimeter cubed to the minus 1, which is moles to the minus 1 decimeters cubed. So in terms of information I've got, I'm going to construct my table. So I've got units. Kc is going to be my equilibrium concentration as well as moles. So initial moles, reacting moles, equilibrium moles, and equilibrium concentration. SO2, O2, and SO3. So my initial moles from the question, I've got 2 moles of SO2, and I've also got 2 moles of O2. I've got no product at the start. At equilibrium, there's found to be 1 mole of SO3, so I've made 1 mole. So reacting, I must have made an extra mole of SO3. Looking at my balancing, it's a 2 to 1 to 2 ratio. Therefore, if I made 1 mole of SO3, I must have used up 0.5 moles of O2, and I must have used up 2 to 3 ratio 1 mole of SO2. Therefore, my equilibrium moles of the reactants are going to be 1 mole for the SO2 and 1.5 moles for the O2. Need to make my equilibrium concentrations. Need to divide by the volume. The volume in the question is 10 decimeters cubed. Concentration is moles over volume. So 1 divided by 10 is 0.1. 1.5 divided by 10 is 0.15. 1 divided by 10 is 0.1. So that's the equilibrium concentrations. Plugging it into Kc, Kc is going to equal SO3 squared, so it's going to be 0.1 squared over SO2 squared, 0.1 squared, times by O2, which is 0.15. Plug in my calculator and I get 6.67 moles to the minus 1 decimeters cubed. On the third question, so we've got an equilibrium between ethanoic acid and ethanol to make an ester and water. So my equilibrium is this. I'll make my Kc expression just at the start. So on top line CH3 COO C2H5 times by H2 for CH3 COOH C2H5OH. If I look at the units there, same expression on the top and the bottom, so it's moles per decimeter cubed squared over moles per decimeter cubed squared. So it's going to cancel out, it's going to be no units here. And if you look at the question, they haven't given me a volume, which kind of backs that up. So putting it into my expression from my table, got the carboxylic acid, got the alcohol, got the ester, which we learn about later on in organic, and water. So I'm going to need to have my initial moles, reacting moles, equilibrium moles, and equilibrium concentration. Okay, so let's look at what we got in the question. So when 1 times 10 to the minus 2 moles of ethanoic acid reacts with 2 times 10 to the minus 2 moles of ethanol, okay, so I'm going to put that's at the start. So trying to trick us a wee bit of standard form here. 1 by 10 to the minus 2 is just 0.01, and 2 times 10 to the minus 2 is just 0.02. At equilibrium, there's found to be 5 times 10 to the minus 3 moles of water. So at equilibrium for my water, I'm ending up with 0.05 moles of water. So assuming I just had these reactants at the start and no products, so I'm starting with nothing there, therefore my water column I've ended up making 0.005 moles of it. Using my ratio, because it's just a nice simple 1 to 1 to 1 ratio, if I've made 0.005 moles of water, I must have made 0.005 moles of the ester product, and I must have used up 0.005 moles of the alcohol, and likewise for the carboxylic acid. Working out my equilibrium moles on the back of that, I've now ended up with 0.005 moles of the alcohol. I've got 0.015 moles of, sorry, that's the carboxylic acid, it's 0.015 moles of the alcohol. I've made 0.005 moles of the ester. And concentration, sorry, I shouldn't have written that last little line because I don't have a volume. So plugging it all into my Kc expression, the concentration or number of moles of the ester is 0.005 times by the moles of the water is the same. Divided by moles of the carboxylic acid is 0.005 also, times by 0.015 for the alcohol, gives me a final answer of 0.33, and as we established at the start, we have got no units for this Kc expression. On to part D, so we're now into imaginary reactions between M, N and P. So if I just look at my equilibrium expression, 2M is reacting with N to go to 4P. Kc expression will just be P to the 4, concentration, sorry, P to the 4, times by the concentration of M squared, times by the concentration of N. So units might be tricky here, so it's moles per decimeter cubed 4 times by moles per decimeter cubed to the 3. So this cancels out nicely, that's just moles per decimeter cubed. Okay, so if I look at my table now, so obviously I've got units to Kc, so I'm going to have to use proper concentrations here. So 2M and N makes 4P. Need my initial moles, my reacting moles, my equilibrium moles, and my equilibrium concentration. So at the start of the question, I've got 0.4 moles of M. Sorry, you can't really see that. and 0.4 moles of N. They react together, and in total volume of 2 decimeters cubed, there's found to be 0.3 moles. So what's not so helpful in this question is the fact they haven't actually told me what it's 0.3 moles of. Now, me doing this in the past, I'm pretty sure it's looking for 0.3 moles of M. Hopefully you doing this in the present, I will have changed that by the time you've done it. But let's just say you found to have 0.3 moles of M. So the equilibrium moles is 0.3, assuming of course that I didn't have any P to start with. So working that through, if I'm now down to 0.3, I must have used 0.1 moles of M. Using my ratio 2 to 1 to 4, if I've used up 0.1 moles of M, I must have used up 0.05 moles of N, and I must have made double that, must have made 0.2 moles of P. Carrying that through, 0.4 take away 0.005, it's going to be is going to end up being 0.35, and adding 0.2 nothing gets you 0.2. Need to divide by the volume to get the concentration. The volume here is 2 decimeters cubed, so it's going to half all these values. Gives me 0.15 mole per decimeter cubed for M. It's going to get me 0.175 moles per decimeter cubed of N, and it's going to get me 0.1 moles per decimeter cubed of P. Subbing that into my Kc expression, so we've got P to the 4, so that's 0.1 to the power 4. We've got M squared, that's 0.15 squared, and then N just by itself, so 0.175. Chuck that all into my calculator, which gives me a final answer of 0.025 units from the start was moles per decimeter cubed. And on to the final part of this question at the start, gives you an equilibrium between carbon and oxygen to make carbon dioxide. So my equilibrium must be this. Give me my Kc expression. Going to put CO2 concentration on the top, and then C. In fact, I'm not now. Something doesn't come up that much in C, and obviously these aren't CA questions, just textbook questions. When you've got a solid in an equilibrium, generally you don't make it part of the Kc expression. You only include gases or aqueous solutions in that expression. So in this case, we're going to ignore C. We're just going to have O2 in the expression. That means, of course, that Kc is not going to have any units because the moles per decimeter cubed will cancel out. But that's our Kc expression here. So effectively what we've really got, we can't ignore the carbon. It's not really part of an equilibrium because it's a solid. We have an equilibrium between oxygen and carbon dioxide. So if I form my table here, so if I go for initial, reacting, and equilibrium moles, and it's between O2 and CO2. Let's see what I've got. At the start, I've got 1 times 10 to the minus 2, which is 0.01 moles of oxygen. Reach the equilibrium at the equilibrium, there are 7.5 times 10 to the minus 3 moles of carbon dioxide, which is 0.0075. So I'm assuming I start with no CO2, I've added 0.0075 moles to it. Therefore, 1-to-1 ratio, I must have used up 0.0075 moles of oxygen. Taking that away from 0.1 to work out what I have at equilibrium gives me 0.0025. At that point, because Kc has no units, I can use the mole values for Kc in place of concentrations. So CO2 in the top, 0.0075 over 0.0025 on the bottom. Gives me a value of 3 exactly. So a bit of a strange one to finish with. Again, I'm not sure it really come up in the CA question, but if you do see a solid taking part in equilibrium with gases, you can leave out the solid from the equilibrium Kc expression. So onto the back page, where we have actually got proper CA Path 0 questions. One little problem, unfortunately, is I'm pretty sure this one we did cover in the notes, so there's no point me going through it now, but obviously you can use it as an extra practice question. We'll go down here. Hydrogen cyanide, blah blah blah, gives you an equation. Ammonia plus methane is equilibrium with hydrogen cyanide and hydrogen. It looks like they're giving me lots of equilibrium values and they're asking me to calculate the Kc in stage units. Probably what we'll do to start off with is just work out what the Kc expression is. So Kc equals the concentration of HCN times by the concentration of H2 cubed over the concentration of NH3 times the concentration of CH4. Working out the units for that, so that's on the top line I've got moles per decimeter cubed to the 4 divided by moles per decimeter cubed squared, which is overall moles per decimeter cubed squared, which is the same as moles squared decimeters to the minus 6. So that's going to come in handy for later. So if I look at my I'm constructing my table here, so NH3, CH4, HCN, and 3H2. Initial moles, reacting moles, equilibrium moles. And in this case, because I've got Kc units, I'm going to need to use equilibrium concentrations. If you look at what's in the question, so ammonia, I've got 0.2 moles at the start, and methane, I've got 0.2 moles of it as well. Place in 1 decimeter cubed container, heated to 500 degrees C, 0.1 moles of hydrogen cyanide and 0.3 moles of hydrogen are produced. So give me two values for the equilibrium moles. So 0.1 moles hydrogen cyanide, 0.3, that doesn't make sense because it's a 1:3 ratio on this equation, so you should have that ratio of your products. If I look at the implication of that, so I had none of this at the start, so obviously made that amount from scratch. So using my ratio, so it's 1 to 1 to 1 to 3, so these must be the same as HCN, so I must have used up 0.1 and used up 0.1. Comparing that to my initial moles, where I had 0.2, 0.2 to start with, must mean my equilibrium moles are just 0.1 and 0.1. Now, I did give an equilibrium concentration row here, but if you look at actually the volume here, it's 1 decimeters cubed. What that means is it's going to do concentration is moles divided by volume, but if I'm dividing by a volume of 1, it's going to say the same value. So it's going to be 0.1, 0.1, 0.1, 0.3. Instead, we're now officially in units of moles per decimeter cubed. Chucking it into my Kc expression, on the top of the fraction, I've got HCn's concentration, which is 0.1, times by H2's concentration, which is 0.3 squared, divided by the NH3 concentration, which is 0.1, multiplied by CH4 concentration, which is 0.1 as well. I can just chuck that all into my calculator. In fact, I've made a mistake. It should be 0.3 cubed. Give me a final answer of 0.27, going back to the units I worked out at the start, moles squared decimeters to the minus 6. On the top right hand side, we got an equilibrium for making Teflon. So we've got equilibrium concentrations. What we'll do first of all is work out Kc. Kc equals concentration of C2H4 times by concentration of HCl squared over the concentration of CHClF2, and that's going to be squared as well. Looking at my units, it's going to be moles per decimeter cubed, and then on the bottom, moles per decimeter cubed squared. It's going to cancel down and end up being moles per decimeter cubed as my units. So doing my working out here, so I'm going to make my wee table. Initial moles, reacting moles, equilibrium moles, and I do have units, so I need an equilibrium concentration. So, if you look at what I have at the start of the question, I've got 0.2 moles of chlorodifluoromethane, which is this one here. I must have none of the products at the start. At equilibrium, I contained only 0.04 moles of the gas. They've been a little bit vague here, but they haven't mentioned any other gas in the question, so they must still be referring to the same gas. So the 0.04 is referring to the reactant. Therefore, the amount that reacted is just 0.2 take away 0.04, which is 0.16. Using my ratio, it's 2 to 1 to 2. So 2 to 1, first of all, I must have used up half the amount of C2H4, which is 0.08. And I must have made exactly the same amount of HCl, so it's going to be plus 0.16. Comparing that to my starting values, must be 0.08 and 0.16 because I started with nothing. To get into equilibrium concentration, we'll need to divide by the volume it's in. So I'm going to divide by the volume of 5 to get all those into concentration values. So the first one is 0.008. 0.08 divided by 5 is 0.016. And 0.16 divided by 5 is 0.032. Now I've kind of ran out of room here quite drastically, but I'll try and squeeze it in here. Kc equals the C2H4 concentration, which is 0.016, times by the HCl concentration squared, which is 0.032 squared, divided by the concentration of the chlorodifluoromethane squared, which is 0.008 squared. In my calculator it goes, end up with a final value of 0.256 moles per decimeter cubed. Then the final question now, this actually was covered in the notes. I'm pretty sure we did one with H2 and I2. No, actually looking a wee bit quicker, it's a little bit different actually, so we'll go through it quickly here. So I've got an equilibrium between H2, I2 and 2HI. If I make the Kc expression very quickly, it's going to be HI concentration squared over H2, I2. Therefore, there's no units to the Kc expression, so it need concentrations. So it's need moles, the initial, the reacting moles, and the equilibrium moles. So at the start, it tells me that equimolar amounts of hydrogen and iodine are allowed to react. Now, this is becoming quite a tricky question because I haven't actually given me any values at all. All it's told me is I've got the same amount of hydrogen and iodine. Now, it's not immediately obvious, but that actually means because you got the same amount of each of the reactants, it doesn't actually matter what you pick for the value. So if you start with 1 mole of each, or 2 moles of each, or 3 moles of each, your Kc wouldn't actually be changed because the effect on the Kc expression would sort of cancel out. So in this case, it's actually easier just to pick 1 mole, but you could actually pick any amount of moles. So I'm going to say there's 1 mole of hydrogen and 1 mole of iodine. That makes it tricky actually. At equilibrium, 75% of the hydrogen by mass are converted to hydrogen iodide. So 75% of this 1 mole that I've just stated must have been used up. Therefore, I must have ended up with 0.25 moles left over. So it's none of this to start with. I must have therefore used 0.75 at 75% being used up. And to 1:1 ratio means I've used 0.75 moles of the iodine as well. 1:2 ratio, therefore I need to double it. Therefore I must have made 1.5 moles of the HI. So given my equilibrium moles now, I've got 0.25 for the I2, I've got 1.5 for the HI. Putting into my expression, I end up with 1.5 squared over 0.25 times 0.25, which ends up with a final value of 36 no units. Explain why the volume of the container is not needed to calculate Kc for the reaction. It's just one marker, so it's enough just to say the Kc has no units. So you could obviously explain that further by saying that the volume would cancel out in the Kc expression because there's no units overall.